All right, so this is part 2 of our Chapter 17 lecture on electrochemistry. So continuing on from where we were, we're looking here now at 17.6, the cell potentials under non-standard state conditions, and the Nernst equation. Now the Nernst equation, it's a funny sounding name, is actually just super, extremely useful. And similar to the equations we saw in Chapter 16, it's going to relate an E cell naught to an actual voltage using a connection to equilibrium. So it's very similar to the equation that we saw before, where delta G was equal to delta G naught plus RTL and Q. Here we're going to get a similar relationship where E cell is equal to E cell naught minus RT over NF, the number of electrons transferred in the Faraday constant, times L and Q, where Q is the reaction quotient. So remembering, though, that if the cell is at equilibrium, then there can't be any voltage. In a similar way that if the cell is at equilibrium, then delta G has to equal 0. If the cell is at equilibrium, E cell, the true cell voltage, not the naught one, the regular one, has to be 0 because it can't be any voltage from a system that's at equilibrium. That requires an actual change going on. They show that there's different versions of this. Some versions use a log base 10. This is more by convention and history. I think it's easier to see the connection between the Nernst equation and the delta G equation that we saw up here with the version that uses the natural logs. But again, this version is also very common and is sometimes provided on standardized exams. So keep in mind that you'll want to use whatever they provide for you in terms of making sure that everything's rounded correctly and such like that. Again, another version of it where they combine all of the variables together. This is another very common way that this equation is written in terms of base 10 logarithms. It used to be that was just so much easier for people to calculate with like a slide rule that this became a very common convention for people to see. But today on a calculator, it really doesn't matter whether I'm calculating a log base 10 or a natural log. I can do them just as easily. So keeping all of this in mind, like the form of the equation you choose is not so important as making sure we understand how to use it and how to solve problems with it. So similarly, we'll calculate a Q value using the provided concentrations and pressures, setting up a system and similar to all the other K expressions that we've used in this course. Plugging in all those values and plugging in the values for the various parameters, we'll look for the number of electrons transferred here, which of course is 2 moles of electrons for this particular cell. The 2 for the zinc goes into the 2 hydrogen ions. And so here we're able to obtain a voltage. Now this voltage is the actual voltage that the cell is producing under these current conditions of concentration. So it's actually a really powerful tool, right? It's hard to measure the current concentrations of things as they change, but it's easy to measure a voltage. So typically, and this is expected when you have batteries, right? That as batteries die, they don't just, the voltage they produce also declines towards 0 in a non-linear sort of way. It kind of comes down at a curve, and this equation helps explain it because it's logarithmic. It's naturally logarithmic, and this comes out of the Nernst equation. The voltages will decline as the cell reaches equilibrium in a sort of logarithmic manner, a decline. Not a jumping up logarithmically, but a logarithmic modeled decline, exponential type of inverse exponential decline. So we expect that if the cell is not at equilibrium and the forward reaction is favored, then there will be a voltage generated. And we could measure this with a voltmeter and confirm it if we built the cell. So here they also talk about the use of the Nernst equation in a pH electrode. So in a pH electrode, they'll build some kind of cell where only hydrogen ions can interact with the electrode and change the conductivity of the surface. And you can use the pH to measure how the cell potential works. Now, you'd think that any ions could affect this E cell or something like that, but no, it's actually tuned to this, and some versions of it have a actual hydrogen electrode in them, different ways they can be implemented. But the basic concept is they measure the voltage of reactions of hydrogen against a standard reference inside the electrode. So they measure this pH electrically with regard to measuring E cell versus a reference, which is what they show here as an example. So they say a higher cell potential indicates a higher pH. So we can use this to measure pH itself, and the hydrogen ion becomes the reference ion for that system. In actual pH measurements, a glass electrode replaces the cumbersome hydrogen electrode they call the calomel electrode used as a reference. It could in theory be other references. It's typically silver chloride with dilute hydrochloric acid like we described. This is all very true. And the tip and the glass of the cell is made in such a way that only hydrogen ions can penetrate into the glass and into this surface so that they can interact with the existing electrochemical system inside it. Okay? And this boundary voltage across the potential for this reaction, which is really slow and has things separated and has a lot of material in it. Some pH meters can even regenerate the material that's in them depending on how the cell is built. But the idea is that we are measuring a cell potential of hydrogen ions against the boundary in order to determine the pH with a pH meter. And this is why, because electrical measurements can be really, really fast, we can make more instantaneous measurements than we could with like a strip, and we also gain a lot more potential accuracy because we're able to measure our concentrations electrochemically. There are other kinds of cells that work similarly to measure other positive ions depending on how you construct the cell, like sodium ions and lithium ions and even ammonium ions. You can build it in reverse and measure negative ions like chloride ions, and they can give you very, very accurate concentrations that can change very quickly with time because it's fundamentally electrical in nature. So they tend to be the standard for measuring these kinds of ions for this purpose. So like here they have this silver wire with silver chloride and a dilute hydrochloric acid. So there's a little potential here. And this separates the test solution from this. And when the glass electrode is immersed, its electrical potential depends linearly on the difference in pH of the solutions on the two sides of this membrane, the internal membrane and the external membrane. So they show how the Ernst equation powers this. They want us to calculate this concentration that will give us this cell. So they're able to look at the cell reaction of the calomel electrode, get a potential. They say the potential has a voltage of 55. They plug this into the Ernst equation, and then they simplify to get the concentration of the H plus ions. They set the partial pressure of the hydrogen gas to 1. That's something else that you would have to be, but this of course is under standard state conditions. They're assuming a standard condition, so we can make that assumption. And that allows us to calculate the pH. Cool and interesting. But this is the basic principle by which the pH electrodes work. You can use different reactions. It doesn't always have to be this one. But the basic principle is being able to measure a gradient across the membrane, this glass electrode. So again, we look here at the delta H naught equation that we've been using previously to convert an standard E cell to a standard delta G. We find that we can also use this other equation that we've seen before for delta G naught in terms of K, substitute in, and rearrange and obtain a new equation where this equation shows that E cell naught is equal to some value. They have this 0.3503 RT. Again, this comes from our natural log of K converted to a log base 10. Again, for simplicity and for standardization. This allows us to calculate E cell naught under standard state conditions given the value of K and the number of electrons transferred, or vice versa. More typically, we're calculating the value of K given the E cell naught that we look up or we measure at standard conditions, and the number of electrons transferred we know should be there from the reactions that we're working with, and K is what is obtained, the equilibrium constant. And similar to before, we can end up with very large values for K. Many redox reactions have extremely large values for K, so sometimes you may not be able to take 10 or E or something to a power in order to appropriately get an answer, so sometimes you're having to leave things in that form. So these are ways that we can obtain the K value, right? We can obtain it directly from concentration data, from thermodynamic data, and also from electrochemical data. So they're showing these are different ways we could obtain K values for our reference purposes and how these kinds of reactions are done. And they also show here how E cell naught varies with the value of K, that when we have non-spontaneous cells, K begins to run in reverse, and for spontaneous cells, under reference conditions, K is greater than 1, and E cell naught is greater than 1. So we look here at the calculation of equilibrium. It's like they say, use this to calculate the equilibrium constant. Yeah, this is typically what's done. So we obtain a value for E cell naught from the various reactions. We make everything balance out. And then we plug in the number of electrons transferred, the voltage, and our other parameters in the equation to obtain the log of K, base 10 here. So 1 by 10 to the 27th power is the value of K, which is huge because we have a voltage here of plus 0.27 volts, so it should be much greater than 1. So here we have a review of batteries. So batteries are just, like I said, a group of electrochemical cells all put together into a compactified way. The simplest and most common, like of the common batteries that people use today, are lead-acid batteries, sometimes called lead storage batteries. They're used in cars. They're car batteries, basically. Car batteries react lead and sulfuric acid to form lead sulfate and water, along with these lead oxides that are also involved in the reaction. The interesting part about this reaction is it's relatively easily reversible by the construction of the cells inside using inert metals and spacers to collect this spongy-like lead sulfate in the presence of water. Applying a voltage can reverse this reaction relatively easily. And that's why these batteries are often used in in cars where you have an alternator, or in backup power supplies where they can take a constant voltage against them to keep them charged all the time. These cells, as much as they contain liquids, they tend to be very heavy, and they're kind of dangerous because they have a lot of very acidic material in them, and lead that's not too good for you either. They're really, really useful because they can produce a very large relative voltage and can be easily recharged with a relatively simple and cheap design. You can compact 6 of these together, and often this creates a 12-volt battery. These can have a lot of capacity too, and a lot of current you can draw, a lot of joules that they can store as well. But if they're plugged in improperly, because they do contain acid, lead, and water, they can explode and can be extremely dangerous. And that's also why these batteries are recycled. They're not good to leave out into the environment. Over time, it's not possible to continue recharging them. They do go bad. But they're really useful for, like I say, for supplying very large voltages for large periods of time, for things like starting a car, which is your typical example use of them, or for rectifiers that need to change DC into AC or things like that, because of their really heavy capacity for recharging. They have a really solid recharge capacity. They can take a lot of recharge cycles. Here we talk about like dry cells. These are like your kind of the precursors to typical alkaline batteries. They're not as commonly used as much today. I have a zinc metal electrode and some copper black. These can generate some voltage as well, depending on which way they're constructed, but they're often used for these D-cell batteries and stuff like that. Again, it's been mostly replaced by alkaline batteries, a modified version in which the acidic one is replaced by a basic electrolyte. Doing this tended to increase the stability of the cell containers, because having acids contained inside metals is generally not a great idea. Acids tend to corrode metals and they tend to leak, but bases tend to be more easily contained inside of metal containers. So they basically rewrote this battery as a basic version instead of an acidic version. These alkaline versions of the cell produce more power and a more stable current because of more efficient ion transport as well. And they can usually be about 1.5 volts. So several of these can be used inside of something to get like 6 and 3 and multiples like that of varying voltage levels. We'll also look a little bit at lithium-ion batteries. Again, I'm not going to test you on any of these battery types specifically, like know how this battery type works, but I might use them in an example or in a problem. And if you're already familiar with the battery type, it gives you a sense of like how something could work, especially the lead-acid battery, because it's really common and its principles are really simple and they fit along with everything that we've already studied. So they're relatively easy to understand. Lithium and lithium-ion batteries can get pretty complex in terms of their structure, and there's a lot of other material science that's needed to understand how they're able to do what they do in the size scales that they do. They're very high voltage in a relatively small space. Typically, the way that they achieve this from a abstract first principle is the use of lithium ions as a charge carrier. Lithium ions migrate through the electrode, and that's the typical thing that they try to achieve that gives them their advantages over other things, because lithium is relatively light, and so it's easy to compactify, and it yields a lot of voltage. As we saw in the standard reduction potential charts, lithium is near the bottom. It's very easily oxidized, but it's also not very stable. So puncturing these and exposing lithium to air can corrode it. They have to be suspended in organic solvents for safety, so there can be a lot of complications going on in here. They talk a little bit more about the distinction between a true lithium and a lithium-ion battery, whereas whether they use a true lithium metal anode or whether they use a graphite anode, again, the idea is using lithium as a charge carrier and how much actual lithium you have in there. You really don't want to have large amounts of lithium because, like I say, lithium reacts with air and water in a particularly kind of violent manner, like other alkali metals like sodium and potassium. These are not particularly safe in large quantities to have exposed to air and water. So it's good to try to decrease that to help increase the stability. But you still need these polymer electrodes and organic solvents and things like that to keep air and water out of these cells, to keep them safe. All lithium batteries have a kind of puncture risk associated with them. And they should be handled with care, especially when they're damaged. They tend to swell up with gas as organic solvents change state and polymers break down, and other reactions tend to happen inside the cell. It's typically how you know that that's the kind of cell these are. When they die, they tend to undergo swelling when they undergo heating or explosion. There's also work to try to use other ions, but lithium ions are really small, so their transport within the matrix is really advantageous, but they can also be, these same basic processes can be done with sodium and potassium, which are much larger, but they're also more stable relatively. So that's another thought of ways, and they're cheaper. You don't have to mine all this lithium as well. So more thoughts in the basic principle, but they're just electrochemical cells like any other cell. Despite how complex they are, you can make them more complex in structure and design, but the basic principle is the same as every principle for every other battery or electrochemical cell. So we'll talk a little bit about fuel cells. These are kind of interesting because they take something that would normally be combusted, like hydrogen gas or methane, typically just burn them directly in an engine, and they turn them into something that can be electrochemically combined instead of being combined with a flame. So these cells are very interesting because they can store hydrogen and bring hydrogen and oxygen together directly through a current electrical connection between the two, and allow the reaction to take place more slowly and in a more controlled manner. And generally, as we discussed when we talked about being close to equilibrium, meaning that you don't have as much loss to entropy, there's a lot of truth to that. When I burn something, I get a lot of heat and light and other stuff I don't really want. I just want the mechanical work out of it. Like in a combustion engine, I want the piston to move. I'm not really concerned about any light that's emitted or stuff like that. That's just a waste as far as I'm concerned. So minimizing the additional side reactions or side processes that can release energy is good, and that helps. That's a good way to do this. Hydrogen gas is very difficult to contain because it's very small and it inculcates metals and it tends to corrode them, whereas if we can combine it into something electrically, then we might be able to store more of it than we could as the true gas and burn it in a more efficient way if we did it electrically instead of as like in a combustion engine like gasoline. So again, this is the basic principle of how this works. And the net formation is the same as if we just burned it, we just get water. We're doing the same thing from a thermodynamic standpoint as we would if we were burning it, which is still a redox reaction. We're just doing it slower and in a more controlled manner. So as a path function, we're changing the path in order to obtain more energy as work instead of as heat. They also talk about making small versions of this that could use methanol instead of hydrogen. And methanol is really interesting because as a fuel, it's also light, and it can also be burned kind of like gasoline, but you don't get as much energy in the engine because it's such a lighter hydrocarbon. But if you burn it electrically, you can get a much higher efficiency out of this, and you don't have to store hydrogen, which can leak and burn and can be a little more explosive. So if you have something that burns slower, that could be better. Again, this is all about the path. But these kinds of cells can store a lot more energy. They store energy more like gasoline than like typical batteries. It's kind of the thought process with fuel cells. You store something more like that. You can generate energies more like a combustion engine than a conventional battery, and you can still have it in a smaller, safer containment type of thing where you don't have to have a true combustion going on. You actually have an electrochemical combustion instead of a flame-based combustion, internal combustion. So here we talk a little bit about corrosion. So typically, the kind of standard for corrosion is the corrosion of iron. Iron turns into rust. And the reason for this has to do with the chemical properties of the iron oxide, the iron 3 oxide, the common iron that forms the orangish kind of rust on things, right? So how does this happen? Well, when water contacts these rusty metals here, exposure in the metal, which exposes fresh metal to the water, air can get dissolved in this water. This helps bring oxygen in contact with iron ions, which can then react to form iron oxide. The iron oxide does not stick to the metal. It comes off and flakes off, exposing more iron and feeding into this process. It says it's been estimated that as much as 1/4 of the steel produced in the United States goes to replace steel structures and products that have been destroyed by corrosion. Turning iron into steel helps protect it. You can put other metals into it to help prevent this process. But iron, despite how strong and great and cheap it is highly susceptible to corrosion because fundamentally its oxide does not adhere to the metal surface. Metals that do have the oxide adhere to the surface include things like aluminum, magnesium to some extent. These metals are very active metals, as we saw on the standard reduction potential chart, but they coat themselves in a protective oxide layer that prevents further corrosion, so they don't rust like this. The corrosion, the oxide layer for iron is just simply not protective. And they show how the stages break down. There's an anode region where iron is oxidized to iron 2+, and then at a cathode region, oxygen is reduced to water with a very positive E cell. Both of these two are very positive. So this process is also facilitated by the presence of acid. The presence of acid can assist in this process. The presence of water to help solvate all these ions can be assistive. The presence of salt to help conduct, to create like a little salt bridge can be helpful. This is why, like, after salty exposure, like cars get salt and stuff on them, it can rust out the metal because of this process. This reaction can be accelerated as long as we make sure that there's specific spots to establish salt bridges. But the cell can be spread over long distances too. Like, we think of a cell as having to be in a beaker or having to be in a battery, but like in reality and in nature, cells can be spread over big distances where a whole region is oxidized and a whole region is a site of reduction. As long as there's a place where some of this happens, then it's able to happen. And it can happen right next to them. They can happen right next to each other too, because there's no wire necessarily for things to conduct through. They say even at pH 7, the potential for the reduction is 8.81, but under acidic conditions, it's even worse. It's even worse. So potential is highly positive, indicative of a spontaneous reaction. And the red-brown material that we call the iron rust. Automobiles rust more rapidly in places where road salt is used commonly to melt snow and ice, because that helps create little salt bridges to help assist in the process. They talk about how aluminum would corrode much faster than iron, but because of the protective oxide layer, we don't see that happening. Like I say, other metals like magnesium, chromium, titanium, and zinc have protective oxide coatings that keep them from corroding on exposure to air, but iron does not. And that's kind of a problem of iron. So you can galvanize iron. You can coat iron with a metal that gets corroded first before the iron that can give electrons back to iron. So if a surface gets scratched, then the zinc gets exposed first. It reacts and in that process it ends up giving electrons back to any iron that might be exposed. So there's a way to kind of use a donor metal so that that metal reacts instead of iron. And as long as it's electrically connected to the iron will pull electrons back from that more reactive metal. Steel used in making automobiles, for example, is coated by dipping it in a bath of molten zinc. This way the zinc corrodes first and feeds electrons back into the oxygen, back into the iron. They have like nails and stuff like that too that are galvanized. They're coated in zinc, and the zinc reacts first, and then it can give electrons back and produce zinc oxides instead of these iron oxides and help protect the metal. Another way they can do this is if they have like buried pipes. What they can do is have a metal cathodic protection, a piece of very reactive metal like magnesium typically, that they bury alongside the iron steel pipe, and they connect it with a wire so that this whole big chunk of magnesium gives electrons back to the pipe as it corrodes, and then they just replace that every so often, and it helps extend the lifetime of this iron-based construction like pipelines and storage bridges. Cathodic protection allows you to easily replace the magnesium when it runs short, and it can keep supplying electrons back to the iron, and it'll be the sacrificial one to keep up the structural integrity for as long as possible. So if we look into electrolytic cells, let's look at these cells, right? We talked about how galvanic or voltaic cells have a positive E cell at a negative delta G. A dead battery is 0. A non-spontaneous cell is also called electrolytic. It has a positive delta G and a negative E cell. So somehow we're going to have to supply power in order to put a voltage in from some other source in order to drive these non-spontaneous reactions. In this example, they have the electrolysis of molten sodium chloride. So they start here with chloride ions in a liquid state, a melted sodium chloride. They put a current through this, and this drives electrons off the chlorine and into the sodium. But you need a high enough voltage to do this. This doesn't just happen with a little voltage. You have to put in oftentimes a very substantial voltage. They call it an overpotential. They'll talk a little more about that. Even more than what the cell would minimally require to set it to 0, you need extra voltage. So not only do you have to apply the missing voltage, the negative part, you have to pull it positive, if that makes sense, in order to make the cell actually run. As in a galvanic cell, the anode is the electrode where oxidation takes place, and the cathode is the electrode where reduction takes place, but the signs are considered typically reversed. So anode is still oxidation, cathode is still reduction, but the signs switch. In a galvanic cell, the anode is considered to be negative, but in an electrolytic cell, the anode is considered positive. This can be very confusing, and not everything follows this nice convention as illustrated in the text, but you should make a note of it as just the typical way that things are doing, because the sign of the electrode in the cell is the same as the sign of the battery to which it's connected. So they're going to connect the battery, the booster, to it, and that's how they base these signs off, the sign that the wire has to be held at by the external source. That's typically the way they look at it. So galvanic, anode is negative, cathode is positive. In an electrolytic cell, the anode is positive and the cathode is negative. Again, it depends on which way they label things. It's not as consistent sometimes as it's made to be. So you can see that when you electrolyze an aqueous salt solution, the electrode reactions may differ from molten one, okay, because now water's involved. So they say that there's a slight preference for oxidation. You would expect a slight preference for oxidation of water in a solution. In a neutral solution, the preference for water oxidation will be greater because the potential at 7 is this. The observed product at the anode, however, is chlorine gas, not water, when you apply, not oxygen gas. So if you put sodium chloride in and you try to electrolyze water, you get chlorine gas instead of oxygen gas, because chlorine comes off first before oxygen due to this overpotential here they talk about. But you will get hydrogen, so you'll get hydrogen and you'll get chlorine, because it's really hard to, reducing sodium is really, really hard, but reducing out the hydrogen is a lot easier. So if you electrolyze water with this salt, you won't get hydrogen and oxygen. You'll get hydrogen and chlorine. That's why it matters which salt you pick as your conductive salt when you electrolyze water, because you may not get the products that you expect. So they talk here about overpotential. That an applied voltage required for an electrolysis is always greater than that calculated. We talked a little bit about that before, how you got to overcome it, you got to make it positive, not just zero. The overpotential needed because of the rate of electron transfer at the electrode solution interface can be slow and limiting the amount of current. For electrode half reaction involving solutions or depositions of metals, overpotential can be small, but ones that produce gases, it can be very high. So it typically is experimentally measured, but it's difficult to bring the oxygen ions as easily to the electrode, the oxygen ions in the OH minus form and for chlorine. So it can be difficult to predict which half reaction will occur for competing ones that are similar. That's a point that needs to be noted, and where they're showing that here is this part. We know the hydrogen will go, but it turns out the chlorine goes before the oxygen, even though the voltage for the oxygen is lower, and you'd think there'd be a preference for the oxygen. It's hard for this reaction is kinetically difficult, and it does seem to be somewhat related. The text doesn't say that, but it does seem to be somewhat related to the number of electrons transferred. It can be more difficult for reactions that need a lot of electrons transferred, like 4 here, compared to these, from a kinetic standpoint, to reach the electrode and react. As long as these voltages are not like hugely different, sometimes you'll get one or the other as a predominant reaction. So they say here, this is the real reaction that ends up happening. So it's a negative 2.19 volts. Sodium acts as a spectator and is not involved at all. The sodium chloride is converted to a sodium hydroxide solution, and chlorine gas is driven off when you electrolyze this solution. That makes sense? They also talk here about the electrolysis of water, finally. Again, they use an inert electrolyte, sodium sulfate. Water is oxidized in preference to the sulfate ion at the anode and reduced to the cathode in preference to the sodium ions. So sodium sulfate is the common salt that's used when you electrolyze water. You put that in the water so the water can conduct within itself. And then you put the 2 electrodes in the water. And water at one side will give up electrons, will be oxidized, and then water at the other side will be reduced. So you'll get a separation of hydrogen and oxygen gases, which is what will evolve in your containers. You'll get 2 moles of hydrogen for every 1 mole of oxygen as this proceeds. So the side that will grow the fastest will be the hydrogen side compared to the oxygen side, which will be lesser. This experiment was used originally to figure out the composition of water itself by 17th, 18th and 19th century chemists looking at the composition of water. Michael Faraday in the 1830s showed that an amount of substance passed through an electrode by electrolysis depends on the quantity of charge. So this is now how we can quantify electrolysis. And I skipped over one part, but this is kind of the last thing we're going to cover here. So if we want to produce a mole, for example, of sodium metal, we'll need to use a mole of electrons to compensate for that. So the more electrons we apply, the more material we're able to pull out of a solution by electrolysis. So charge in coulombs is equal to the current with time. Current is in amps, and amps is coulombs per second, so we multiply time by current to get charge. So this is where current is related to the amount of stuff. We talked a little bit about that earlier. And moles of electrons will equal the charge times the divided by the coulomb, the constant, the Faraday constant here. So we'll look through and work at an example. It shows a basic process of how we would work this out. If we know the current and time, we can get the charge, moles of electrons, moles of products, grams per liter of product. Now different problems will give you different things to start out with, like they'll give you a time or they'll give you an amount they want or something like that, but the basic problems all work out the same way. So here they give us a current of 30 amps passed through an aqueous solution of sodium chloride for 1 hour. And they say how many grams of sodium chloride and how many liters of chlorine gas at STP are produced. Okay, so first I'm going to convert the charge into coulombs, and use this to get the moles of electrons that I'm going to have. So then I'll just set up the two reactions that I'm interested in and say that these reactions need to occur these number of mole of electron times. But if this is a 2-electron transfer, then I'll need to make sure I convert this right. So they say here that I'll get 2 moles of sodium hydroxide based on the 2 moles of hydroxide here, and 2 moles of electrons that I need to apply in to convert these moles of electrons into moles of something else. So I just use the electrons like they're a product or reactant in my reaction to get moles of sodium hydroxide based on this hydroxide number, then just convert that into grams using the molar mass, and I've got it. Then over here I use the other reaction, treat the electrons as though they are, a product here, convert between the two products to convert it to chlorine gas. Here there's only a 1 coefficient for the chlorine, so we'll get half as many moles of chlorine gas as we did electrons we put in, because it costs 2 to make one of these. Then once we have moles of chlorine gas, we can use the ideal gas law, or remembering that a mole of any ideal gas occupies 22.4 liters at STP, multiply those and get 12.5 liters of chlorine gas. You can also take this out as one step like they show here. Now, I like the way they write this out, because some problems they won't give you a time, or they won't give you the current, or they won't give you something. So it'll depend on what step here, but this basic workflow will work. You'll just need to substitute in perhaps a different step in the process. They may ask you how much time does it take with a certain current to get a certain amount of metal. So you'll want to just convert that back into moles, get to moles of electrons, get to charge with the time, in order to calculate, what other piece that you need. Maybe it's the time piece that you're trying to calculate or something like that. Here I look at another example that works similarly here. They say, how many amps must we pass through the cell to produce sodium metal at a rate of this? Okay, so first we need to calculate the number of moles of sodium produced per hour by converting the kilograms into moles. So that's how many moles I need per hour. To produce each mole of sodium, I need 1 mole of electrons. So then I can say this is the charge passed through, which is this same number of moles converted into coulombs. And then they say I need 1 hour, so I get 3,600 seconds in an hour. And then easily here I can calculate the current that's required. So again, that's just some example review problems. There may be other ones on electrolysis to review, but they'll work basically in the same flow. Well, I hope you found this lecture edifying and interesting, and I hope to see you all again in the next one. Thank you so much for your time, and I will see you later. Bye-bye.